Good morning. So, what we're going to do in today's lecture is to begin discussing alkyl halides. And this actually is now going to be something that will continue for the remaining 7 lectures of the class, where we're going to be looking into and trying to understand the varied reactivity of alkyl halides. So what we'll do today is to start looking at how we name them, and more importantly than how we name them, really what the anatomy is of different alkyl halides. And then we're going to return to those nucleophilic substitution reactions that we've used in some previous examples in talking about rates of reaction. Try to understand a little bit more about their mechanism and their anatomy, what the various components are and what's going on in them. And then we're going to look, if we have time, at some analogous examples. And then over the remaining lectures of the class, we're going to start to look into varied reactivity patterns as you change the structure of alkyl halide, and also some of the really exciting stereochemical implications of this. So let's begin by talking about the nomenclature of alkyl halides. And the good news about this is it's really very similar to the nomenclature of alkanes. You simply name them as the haloalkane. And I'll show you what I mean. So basically, just as we learned that you could have on the quiz a methyl substituent or an isopropyl substituent on an alkyl chain, as we had in our example of isopropyl methyl decane, you can have various halogen substituents, fluorine, bromine, chlorine, and iodine, on an alkyl chain. So let's just take a couple of examples of this. So you're going to name them as the haloalkane. You'll number and alphabetize the substituents. So you're going to number and alphabetize, and of course you'll be alphabetizing under fluoro, chloro, bromo, iodo. If you look in your periodic table, you'll see there's one more element that falls into the halogen family, one that we absolutely never see in alkyl halides. Which one is that? AT. What is that? Astatine. It's radioactive. There are no stable isotopes of it. And organic chemists, although we actually like to play with molecules that are radioactive. For example, radioactive carbon is used in drugs for PET scans. Nobody, to my knowledge, has yet found any application of astatine in any sort of organic compound, which probably means that your generation should be the one to do it. Anyway, we'll concern ourselves with fluorine, bromine, and iodine. And then you number these and alphabetize them along with the alkyl substituents. In other words, as far as the nomenclature goes, there's nothing special about it. I'll just take a couple of examples here. We'll see what I mean. Just a few simple ones. And as I've indicated before, although there's certainly entire books that can be written on nomenclature, I think beyond the basics, beyond getting the gist of picking the substituents, picking the main chain, and alphabetizing, and knowing a few of the substituents that we saw, like isopropyl and terbutyl, I think it really gets to be an exercise in futility. So this compound here, we would say, okay, we have a 5-carbon chain. We have a bromine substituent. We can number the chain from either direction, but we're going to number this chain to put the bromine at the lowest position. In other words, we're going to number 1, 2, 3, 4, 5. This compound is 1-bromopentane. And if the bromine were at the second position, we call it 2-bromopentane. Here's another example. So this compound, you pick the longest chain. Well, no matter how you slice it, the longest chain is going to be 3 carbons. Doesn't matter whether you number this way or whether you number this way or whether you number this way. And the substituents on the chain are going to be a chlorine and a methyl group. So both at the 2 position. So the compound's going to be 2-chloro, 2-methylpropane. And as is often the case, many compounds have common names, trivial names that sometimes are so widely used that they are the things that really will roll off the tongue of a practicing organic chemist. When I write out these names, I'll try to remember to put them in parentheses just to make a distinction for your notes. So this one, what would roll off of most of our tongues would be tertbutyl chloride. Take one more example, and I'll give us a cyclic example with some stereochemistry just to remind us. Bring back some concepts of stereochemistry. This one also gives us some of our nomenclature of substituents. Okay, so we named this compound as a cyclohexane ring. You have an iodine on the ring, you have a tertbutyl group. Remember, if you're numbering and everything else is equal, you're just going to number to give the lowest number to the first substitution. In other words, here we honestly could number either 1, 2, 3, 4, or 1, 2, 3, 4. Everything else is equal because it's not the first substituent on the chain. And in this case, since butyl becomes before iodo, we'll number this as 1, 2, 3, 4. And so this compound becomes 1 tertbutyl, 1 4-iodo cyclohexane, and more specifically, we indicate the stereochemistry. Cis 1 tertbutyl, 1 iodo. All right, what's much more important than how we name these compounds is really how we think about them. And what we're going to see as we go through and look at SN1 substitution reactions and SN2 substitution reactions and E1 elimination reactions and E2 elimination reactions is that we need to understand the anatomy of them. Whoops. Yes. Thank you. Always a sharp pair of eyes. Always very much appreciated. All right. As I was saying, what's much more important is really figuring out the anatomy of these compounds. And so I'm going to spend a few blackboard panels actually writing out some different alkyl halides. Because the first thing you'd look, oh yeah, it's just a compound with some halogen on it. So let's look at some anatomy here. should become good enough at visualizing this that we really see this right away, that you don't have to go to any sort of rule book, that it basically just comes to your mind right away. So that's why I'm going to go slow. All right, so CH3CH2I, the one we used in our example of an SN2 displacement reaction with cyanide. Obviously, it's an iodoalkane, but what's much more important about this is that it's a primary iodoalkane. So I'll write its name just to remind us, iodoethane. No need to number, because no matter where you put the iodine on the ethane, it's always going to be at the one position if you don't have anything else there. But much more important, the iodine is attached to a primary carbon. Remember, a primary carbon is one with one other carbon attached to it. Primary, and we often abbreviate this 1,0 alkyl halide. The general structure, if you're looking for sort of a general structure, what's going to clue you in that you have a primary alkyl halide? It's going to be that you have whatever your chain is, whatever your R group is here, we'll see various examples, bound to a CH2 group, bound to a halogen. And again, that halogen could be fluorine, bromine, fluorine, or iodine. Fluoro compounds actually react a little bit differently than bromo, chloro, and iodo compounds. There are a lot of reactions that chloro, bromo, and iodo compounds take part in that fluoro compounds don't. And when we come to our discussion of leaving groups and relate this concept to pKa's of the conjugate acid, remember we said HF was a very weak acid compared to HCl, HBr, and HI. We'll see the differences in reactivity. Anyway, right now what I want us to do is just to focus on the fact that we have a methylene group, a CH2 group, connected to our halogen, and see that aspect of the anatomy. And let's contrast this with the other one that we took, PH3CBr. Remember, pH was that shorthand that we used for phenyl, so it was 3 benzene rings. I wrote this out before, but I'll write it out again. If you have it in your notes, don't bother to retranscribe it. Just to remind us, since we do get a few abbreviations. All right, so when you look at this, it takes a moment to make sense. We have a carbon with 3 other carbons attached to it, and so that's a tertiary carbon. And so this is a tertiary alkyl halide. So I'll write out the name, bromo-triphenylmethane. If I had more space, I wouldn't be using a hyphen. I'd run the triphenyl directly into methane. And I'll point out that it's a tertiary alkyl halide. And the general structure that's going to clue us into something being a tertiary alkyl halide is we have a carbon with 3 other carbons attached. So I'll write this in shorthand as R3CX. more examples, and then we'll get the catalog of all of our types of alkyl halides that you'll see for the basic ones, and then I want to draw some really important contrasts. All right, let's take this one. This is Chloro Cyclohexane. No need for a number on it, just like Methyl Cyclohexane. There's only one. You just have a chlorine, no matter where you put it. It's always by definition at the 1 position. Chloro Cyclohexane is a secondary alkyl halide. And what clues us into it being a secondary alkyl halide, what makes it a secondary alkyl halide, is the chlorines attached to a secondary carbon. In other words, a carbon with 2 other carbons attached to it. If I wanted to write a generic structure, I could write it as R2CHX, and that would be a generic one, again, with any of your typical halogens. We're going to see that all of these classes that we're looking at have very different reactivities. And the reason we're spending this time is so that we see the anatomy, because these are going to tie into the patterns of reactivity that the compounds undergo. Tertiary alkyl halides tend to undergo SN1 reactions and E1 reactions. Primary alkyl halides tend to undergo SN2 reactions and E2 reactions. Don't worry about getting that down right now. We're going to come back to that. The last one in this sort of general categories of alkyl halides are the methyl halides. So if we take CH3I, iodomethane, and here's one where I'll write the common name, because probably off of Johnny's tongue or Buck's tongue in the laboratory, they would refer to it as methyl iodide. As a matter of fact, you probably see that on the bottle in the laboratory as well. And so for our methyl iodide, this is a little special. It's not a primary alkyl halide. It's a methyl halide. And we'll learn that they fall into their own special category. They're extra reactive in SN2 reactions. General structure CH3X. For all intents and purposes, there are just 3 or 4 of them, and you're probably never going to see them. All right, what I'd like to do now is to show you a couple of what I'll call special types of halides. And the reason I'm drawing emphasis to this is where students often get confused. So I'll put this in parentheses. Because it's very easy to look at some of these and get mixed up on what's going on. So, let's suppose we have a halogen on a benzene ring. Let's take this with a bromine. This is bromobenzene. All right. This isn't an alkyl halide. Benzene isn't an alkyl group. It's an aromatic group. And the reason I'm telling you is not that I want a gotcha for you, but nature has made this gotcha where phenyl halides are completely different in their reactivity than all of the alkyl halides. And there are a lot of reasons for this. You're going to learn about it later. One of the reasons for this is all of the SN1, SN2 reactions involve a nucleophile getting in behind the halogen. And that can't happen. But more important, it's an issue of hybridization. We're using an sp2 hybrid bond to make a bond to the bromine here, not an sp3 hybrid orbital to make a bond to the bromine. And the bond is much stronger, the hybridization is different, and the reactions occur in a very different fashion. So this is a phenyl halide. It's not, and how big can I write the word not? Secondary. Or tertiary. You might look and say, well, I see 2 carbons bound to it. It's a 2, must be secondary, or I see a double bond here, or you learn to count that as 2 carbons in Coning-Gold Prelog. But it's just not. It's not an alkyl halide. It's not secondary. It's not tertiary. And again, I'm just going to write a big fat not over here. Doesn't react like an alkyl halide. Nature, again, makes very different rules of reactivity, where all the simple stuff that you see for primary halides or secondary halides simply doesn't apply. And I'm just doing this as an example. Any example of a halogen bound to any sort of double bond, or for that matter, I might add a triple bond, doesn't react in the same way. This compound is called chloroethene. This ENE on the end comes from nomenclature of alkenes. You're going to learn more about that nomenclature when you come to alkenes. Again, Buck or Johnny probably wouldn't refer to this compound by this name. Often with small compounds, common names, trivial names become more widely used. I'll put the common name vinyl chloride in parentheses. Ever heard that name before? Vinyl chloride. Heard it with something in front of it? Polyvinyl chloride, PVC pipe. So this is the monomer. So many compounds that you encounter in your day-to-day life are made up of simple chemicals that you're seeing. Polyethylene is actually a polymer of ethylene that in the polymerization process makes it into a great big long alkane. Linear or branched, depending on whether it's high density or low density polyethylene. But basically little monomer units connected together. And this vinyl chloride is the monomer that gets polymerized together to make PVC. All right, this, like chlorobenzene or bromobenzene, is not an alkyl halide. It's a vinyl halide. Vinyl is the common name for double bonds, the trivial name, and you'd probably refer to them generically as a vinyl halide. So it's not primary. And again, I'll write the biggest bold as not I can. not primary, not secondary. It's just not an alkyl halide. And again, just like the case of bromobenzene, it doesn't react like an alkyl halide. All right. And this is really about seeing the anatomy of these molecules. So here we're bound not to an sp3 carbon, but to an sp2 hybridized carbon. And as I've indicated before, since chemists always like, when confronted with rules that nature provides, chemists always like to poke and prod at those rules. Chemists have indeed tried to check and poke and prod. Can we make this compound, can we make a vinyl halide react like an alkyl halide? And for the most part, the answer really is no. They simply don't want to take part in SN2 reactions. All right. Now, also to avoid some confusion while we're talking about what I'll call as special types of halides, two that might confuse you, and so I want to get them up here explicitly. Let's take this one. Is this an alkyl halide? Yes. Why? It's attached to a alkyl carbon, primary carbon. Yeah, this is a alkyl halide. It's a primary alkyl halide, and its reactivity is actually very much like this. So this compound, I won't even write out the non-trivial name. I'm just going to write the trivial name. Benzyl Bromide. So this is primary because we have a CH2 group, so it's an sp3 hybrid. That's telling us it is an alkyl halide. So this is RCH2X. So this is a primary alkyl halide. And the only thing that's special about it is it's what we would call benzylic. And what that means for various reasons is it's actually a little bit extra reactive. In SN2, and depending on the substitution pattern, SN1 or even E2 elimination reactions. This one can't undergo any elimination because there are no beta hydrogens, but we'll get examples later on where there are. But anyway, the main thing, if none of that makes sense to you right now, the main thing is to recognize that there's a profound difference in structure between bromobenzene and benzyl bromide. One of them's an alkyl halide, the other one is not. And I'll give you one more example that falls into the same category. And again, I'm just going to, for the sake of simplicity, I'm just going to give you the trivial name on this. Alkyl iodide. And of course, one of the reasons why I want us to notice the trivial name is this is actually an archetype here. So in general, this class where you have a halogen 1 over from a benzene ring on an alkyl carbon that's connected to it would be called a benzylic halide. And this one we would call an allylic halide. So this is a primary alkyl halide for just the same reasons. And what makes it a little bit special is it's an allylic halide. That means that the halogen is not on a double bond, that would be a vinyl halide, but is on an alkyl carbon 1 over from a double bond. And just like a benzylic halide, it's a little bit extra reactive. What the implications are of this as we go through SN2 and SN1 and E2 and E1 reactions, what the implications are is that reactive ones and extra reactive ones are going to take part in reaction with reagents that we're going to see, nucleophiles and bases. Whereas ones like bromobenzene and vinyl chloride are not going to react at all with these reagents under normal conditions. Didn't get me on the head. All right, where do I want to go? All right, let's now, because I've been talking at reactivity and we've been creeping around this issue for a while in our discussion of Chapter 6. Let's revisit the two reactions that we talked about in Chapter 6. These are nucleophilic substitution reactions, and then what we're going to do is generalize these. To look at other examples of alkyl halides and other nucleophiles. But let's start with the two examples that I had written out before. So the two examples that I wrote were iodoethane reacting with cyanide anion. I'll write it with the negative charge on the carbon, giving us propionitrile plus iodide. And the related example that I wrote of triphenyl methyl bromotriphenyl methane reacting with cyanide anion, giving us the corresponding nitrial plus bromide. All right, these are both substitution reactions, and of course by substitution, I mean that one group is replacing another. In both of these examples, cyanide is replacing a halide. Now let's take a moment then to talk about the anatomy of the two components in this reaction. In both of these reactions, the component that's doing the substituting, the component that's coming in, we refer to as a nucleophile. So the cyanide in these examples is a nucleophile. Nucleophile is something that has electrons that it wants to share. It's a Lewis base. It's something that likes a nucleus, a positive charge, hence it has electrons, it has the negative charge that it wants to share. And it doesn't have to have a negative charge. Just like we saw Lewis bases that had a negative charge on them, but we also saw Lewis bases that had no charge on them. All a nucleophile has to do is be willing to share its electrons. Now, conversely, these components that like the electrons, we're going to call electrophiles. Electrophile is what we learned as a Lewis acid. This is why when we started discussing acids and bases, I said taking this organic flavor and looking at the reactions of organic compounds made so much sense in differentiating ourselves from general chemistry, because there is this much broader principle of reactivity that so many organic reactions involve the reaction of a species that has electrons with a species that wants electrons. And of course, the formation of bonds involves simply the sharing of a pair of electrons. All right, one more piece of anatomy. The iodine, the bromine, we refer to as a leaving group. And I would typically refer to them as a leaving group both after they've left, but also before they've left. So I'll write leaving group next to them. And again, to come back to this really important distinction, because we've just seen a whole bunch of different drawings of different halides, both alkyl halides and non-alkyl halides. To refocus this, the common feature in all of these substitution reactions is that the carbon that's getting substituted at is an sp3 hybridized carbon. All right, so here I've reminded us of all of the things that these two reactions have in common. Now what I want to do is focus on the differences. And the big difference is that the electrophile in the first example, the iodoethane, is a primary alkyl halide. And the electrophile in the second example, the bromotriphenylmethane, is a tertiary halide. So the first reaction, as we saw, because we use these when we discuss mechanism, is occurring in an SN2 reaction manifold. And I mentioned that term, but I didn't write it out on the blackboard before. I just showed us the differences in reaction. So an SN2 reaction, SN2 stands for substitution, nucleophilic bimolecular. An SN2 reaction, as we saw before, is a concerted reaction. The mechanism involves the cyanide, the nucleophile, and I'll draw in one lone pair in the cyanide, coming in. Remember, electrons flow from the nucleophile to the atom. We break the bond, we put electrons back on the atom. So the reaction involves two molecules coming together in a concerted fashion. It occurs in a single step, with no intermediate. And we saw before that as the atoms come together, as the cyanide approaches the ethyl iodide, we go through a trigonal bi-pyramidal transition state. Remember, the transition state is that fleeting arrangement of atoms that exists for only about a femtosecond, for only about 10 to the minus 15 seconds, where one atom is coming in and forming a bond, the nucleophile is coming in and forming a bond, it's pushing out, it's substituting for the leaving group, and that bond is breaking. The carbon at the reaction center, in this case the primary carbon, has gone from being tetrahedral to being trigonal planar. I've drawn it so that the carbon is lying in the plane of the blackboard with the hydrogen coming out. We're starting to form our bond to cyanide. We're starting to break our bond to iodine. We have part of our negative charge at cyanide, part of our negative charge at iodine, and I'll just bracket this and use our little double dagger symbol to remind us that this is a transition state. And we saw in our discussion of Chapter 6 that there were kinetic implications of this. In the rate-determining step, two molecules are coming together. And so the rate law for this reaction is that the rate is equal to the product of the concentration of those two reactants. Concentration of ethyl iodide and the concentration of cyanide anion. Double the concentration of either of those, the reaction goes twice as fast. Double the concentration of both of them, and the reaction goes 4 times as fast. This transition state's really cool. We're going to see all sorts of stereochemical implications of it as we go on in our discussion of SN2 reactions. All right, the second example. The second example is an SN1 reaction. SN1 stands for substitution nucleophilic unimolecular. And we've already seen the mechanism for this reaction. The reaction goes in 2 steps by way of a carbocation intermediate. Remember, in the first step, the halogen leaves. We get a triphenyl methyl carbocation. So here's our first step, PH3CBr. And the bromine leaves. It takes its pair of electrons with us. I'll give us just a little abbreviated drawing of the mechanism there, showing the arrow going on to the bromine. In the second step, our cyanide comes in. Cyanide's a nucleophile. It has electrons to share. You darn well know what wants the electrons. The carbocation is unhappy. You have a carbon that only has 6 electrons around it, and it wants 8. So cyanide comes in. And again, I'll give you an abbreviated mechanism just showing our cyanide coming in, and I'll draw the bond to the carbon and be good about that. The cyanide coming in and reacting to form our new bond. And as I said, the important feature of this reaction is the first step is the rate determining step. We saw this before when we discussed the kinetics. That means that step occurs slowly. As soon as you form the carbocation, it finds a nucleophile and very rapidly collapses down to a new stable compound. So I'll write fast. So whereas an SN2 reaction showed bimolecular kinetics, an SN1 reaction shows unimolecular kinetics. In other words, the rate of reaction is equal to K times the concentration of bromotriphenyl. All right, thoughts or questions at this point? SN1, great question. SN1, is it always going to go by a carbocation intermediate? Every example of an SN1 reaction that I can think of will go by way of a carbocation intermediate. Other questions? All right, this is a great point for us to stop. We will pick up next time talking about